So in the previous chart, we talked about uniform circular motion, and I showed you a picture of some gum stuck to the rim of a bicycle wheel, which is rotating, in this case, in a counterclockwise direction. And in this chart, we want to talk about the idea of a radian for angular measure and how radians can be used to relate angular and linear velocity. And so first of all, let's define something called the period. I'm going to use a big T for that, which is the time for the gum to go around once. In other words, it would be the time for the gum to go all the way around at whatever angular rate it's going and then return to where it started. And typically we'll express this in seconds, but it could be any unit of time. And you should know from your previous math that going once around corresponds to the this radius spoke here. Let's say it's a spoke in the wheel rotating 360 degrees. And typically we won't use degrees for angular measure. We'll use radians, and there's 2 pi radians in 360 degrees. And so from that you can see that radians are a larger angular measure than degrees. In fact, if pi is equal to 3, you have roughly, very roughly, 6 radians is equal to 360 degrees, which means a radian is roughly equal to 60 degrees. It's rather large. So the angular velocity, if it goes once around in time, big T, is going to be 2 pi rads, that corresponds with once around, divided by t seconds. T is the period, the time it takes to go around once. And so that would be 2 pi over t rads per second. That is the angular velocity, and we're going to call this omega. It's a new Greek letter. Angular velocity, we use velocity because the convention is that if it's rotating in a counterclockwise direction, that's considered to be positive. If it's rotating in a clockwise direction, that's considered to be negative. So what I have shown here is counterclockwise, CCW. And so this would correspond to a positive omega. The linear velocity is at the instant shown. It's in the direction of the screen vector, which is a tangent vector to the circle. And the linear speed, which would correspond to the magnitude of this linear velocity, is the circumference of the circle divided by the period. And in other words, the way to think about that is, if it goes around in time t, the distance traveled is the circumference, and the time taken to travel that distance is t, the period. So therefore the linear speed is 2 pi r, the circumference, divided by t. But we can take this and break it up into 2 pi divided by t times r, which is omega times r. And therefore the formula for the linear speed is, let me write it here, v is equal to omega times r. This is linear speed. This is angular speed, which must be written in radians per unit time. The time you use isn't critical, but the fact you use radians is times the radius. It comes right out of this formula here. Note one little subtlety here. The units of linear speed are meters per second, and the radians in omega have disappeared. And so radians, when they're combined with linear and other units, disappear. So it's simply meters per second. Okay, last point. Although the linear speed is constant, the linear velocity is not, since the velocity direction changes. You can see that by looking at this picture. If you went to another location on the rim, so let me just draw one here. Let's say the gum is rotated from here over to here, then the linear velocity would then be a new tangent vector just as long as the other one, but pointing in a different direction. And so the velocity isn't constant because its direction changes. And since the linear velocity is not constant, the acceleration is not equal to 0.